Right now, as you're watching this video, something extraordinary is happening in the depths of space. Roughly 2 billion light years away, a black hole is devouring matter equivalent to an entire sun every single day. The energy it releases in just 1 second could power human civilization for trillions of years. And that's not even close to being the most powerful thing out there. Tonight, we're embarking on a journey to the absolute extremes of cosmic power, where the forces at play are so incomprehensibly violent, they challenge everything we thought we knew about the limits of energy and destruction in our universe. Before we dive into this cosmic tour of ultimate power, I'd love to know where you're tuning in from tonight, and what keeps you staring up at the stars in wonder. And if you find yourself drawn to these mind-bending cosmic mysteries, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of cosmic explorers. Get ready. The journey begins now. We live in a universe where the word powerful takes on meanings that stretch human comprehension to its breaking point. When we talk about power here on Earth, we might think of nuclear reactors, volcanic eruptions, or the most devastating hurricanes. But these pale into insignificance when compared to the cosmic engines operating in the depths of space, where single events can release more energy than our entire galaxy produces over centuries. The question we're wrestling with tonight isn't just academic curiosity. Understanding the most powerful forces in the universe helps us grasp fundamental truths about reality itself. These extreme phenomena serve as cosmic laboratories where the laws of physics are pushed to their absolute limits, revealing secrets about space, time, matter, and energy that we could never uncover here on Earth. But here's what makes this exploration truly fascinating. The contenders for most powerful thing in the universe operate on completely different scales and through entirely different mechanisms. Some concentrate unimaginable energy into spaces smaller than cities. Others spread their influence across billions of light years of space. Some last for mere fractions of a second, while others have been operating since the universe was young. Let's start our journey by establishing what we mean by power in the cosmic sense. Power, fundamentally, is the rate at which energy is released or transferred. But in space, we encounter energy releases so extreme that they require entirely new ways of thinking about what's possible in our universe. We're talking about events that can outshine entire galaxies, bend the fabric of space-time itself, and send shockwaves rippling across cosmic distances. The challenge facing astronomers trying to measure these phenomena is staggering. How do you quantify the power output of an object billions of light years away? How do you comprehend energies measured not in watts or joules, but in units so large they require scientific notation with dozens of zeros? The tools and techniques scientists use to study these cosmic powerhouses represent some of humanity's greatest technological achievements, from space-based telescopes that can detect the faintest whispers of ancient light to gravitational wave detectors sensitive enough to measure distortions in spacetime smaller than a fraction of the width of a proton. As we explore each contender for ultimate cosmic power, we'll discover that the universe operates on scales that challenge not just our technology, but our very ability to conceptualize such extreme conditions. We'll encounter objects so dense that a teaspoon of their material would weigh more than Mount Everest, explosions so bright they can be seen from the edge of the observable universe, and forces so fundamental they literally hold reality together at its most basic level. Our first stop on this cosmic tour takes us to what many consider the universe's ultimate powerhouses, black holes, but not just any black holes. We're talking about the supermassive monsters that lurk at the centers of galaxies, some containing the mass of billions of suns compressed into regions smaller than our solar system. First, consider TON 618, one of the most massive black holes ever discovered. Astronomers estimate its mass at approximately 66 billion times the mass of our Sun. Its event horizon, the point of no return, where even light cannot escape, spans roughly 1,300 astronomical units. To put that in perspective, our entire solar system, from the Sun to Neptune, spans only about 30 astronomical units. That means TON 618's black hole is more than 40 times larger than the solar system, but TON 618 may be second in line. Enter Phoenix A star, the supermassive black hole at the heart of the Phoenix cluster. Some unconfirmed models suggest it could have a mass of 100 billion solar masses, potentially outsizing TON 618. If that estimate holds, its event horizon would stretch approximately 3,900 astronomical units, or more than 100 times the size of the solar system. Now, if our Sun was scaled down to the size of a grain of sand, how big would Phoenix A star be? In that scale, the black hole would be truly colossal, the equivalent of a large city, or possibly even a small metropolis. It would dwarf any familiar structure on Earth, spanning such an immense region that it defies normal human comparison. These supermassive black holes demonstrate power through what physicists call gravitational binding energy. The deeper you fall into a gravitational well, the more energy is released when matter accelerates toward the black hole. At the event horizons of objects like Phoenix A star and TON 618, infalling matter reaches significant fractions of the speed of light, releasing kinetic energies that dwarf any other natural process we know of. But the power of supermassive black holes extends beyond just their accretion processes. Many of these cosmic giants produce jets of plasma that stream away from their poles at nearly the speed of light. These jets can extend for millions of light years, carrying energy and magnetic fields across intergalactic space. Recent observations have revealed jets so powerful they affect the structure and temperature of the cosmic web itself, the largest scale structure in the universe. The jets from supermassive black holes represent one of the most efficient energy transport mechanisms in nature. Powered by the rotation of the black hole itself and the magnetic fields threading through the accretion disk, these jets can carry away enormous amounts of energy over vast distances. Some jets have been observed to maintain their coherent structure across distances of several million light-years, a testament to the incredible forces that create and collimate them. What makes these black hole systems particularly impressive is their longevity. While other cosmic powerhouses might release enormous amounts of energy in brief bursts, supermassive black holes can maintain their prodigious energy output for millions or even billions of years. They represent steady-state cosmic engines, converting matter into energy with relentless efficiency across cosmic timescales. The discovery of supermassive black holes has revolutionized our understanding of galaxy formation and evolution. These objects don't just passively sit at galactic centers. They actively regulate star formation, gas flows, and the overall development of their host galaxies through their powerful feedback mechanisms. The energy they inject into their surroundings can shut down star formation across entire galaxies, demonstrating how the most powerful objects in the universe can influence cosmic evolution on the largest scales. Yet even these cosmic giants face competition from phenomena that, while perhaps not as long-lived, release energy at rates that challenge our understanding of what's physically possible. As we continue our exploration of ultimate cosmic power, we'll encounter objects that pack the energy equivalent of entire stellar explosions into timeframes measured in seconds, and forces so fundamental they literally determine the fate of the universe itself. The story of cosmic power is far from over. In fact, we've only just begun to scratch the surface of the extreme forces that shape our universe. As we delve deeper into this cosmic hierarchy of power, we'll discover that the competition for most powerful thing in the universe is far more complex and fascinating than any single answer could capture. The universe has been conducting experiments in extreme physics for nearly 14 billion years, and the results are nothing short of spectacular. From the crushing forces that forge atomic nuclei to the mysterious energy that drives cosmic expansion itself, we're about to explore phenomena that push the boundaries of power to their absolute limits. Our journey into ultimate cosmic power has only just begun, and the most mind-bending discoveries still lie ahead. But to truly understand ultimate cosmic power, we need to venture beyond the steady engines of supermassive black holes into realms where energy release defies every intuition we've developed about how the universe should behave. We need to explore phenomena so extreme that they rewrite the rules of physics in real time. Picture this scenario unfolding somewhere in the distant cosmos right now. A massive star, perhaps 50 times more massive than our Sun, has been burning through its nuclear fuel for millions of years. Deep in its core, silicon atoms are fusing into iron at temperatures exceeding 3 billion degrees. But iron represents a nuclear dead end. Unlike lighter elements, iron fusion consumes energy rather than releasing it. As the star's core fills with iron, nuclear fusion can no longer provide the outward pressure needed to balance the crushing force of gravity. What happens next unfolds in a time frame so brief it challenges human comprehension. In less than a second, the star's core collapses from the size of Earth to a sphere barely 20 kilometers across. The density skyrockets beyond anything found elsewhere in nature. Protons and electrons are crushed together to form neutrons, releasing a flood of neutrinos that carry away more energy than our Sun will produce in its entire 10 billion year lifetime. This is the birth of a supernova, and we're about to witness power release on scales that dwarf even the most extreme black holes. The collapsing core rebounds in a shockwave that tears through the star's outer layers at speeds of 30,000 kilometers per second. The explosion that follows can outshine an entire galaxy containing hundreds of billions of stars. But here's what makes supernovae truly remarkable from a power perspective. While supermassive black holes spread their energy output over millions or billions of years, a supernova concentrates the equivalent energy into a time frame measured in seconds to minutes. We're talking about power outputs that reach 10 to the 44th watts. To put this in perspective, this single exploding star briefly generates more power than a trillion of our suns combined. The energy mechanisms driving supernovae reveal themselves through multiple channels. The initial gravitational collapse releases binding energy, equivalent to several solar masses converted directly into kinetic energy and radiation. The nuclear burning that continues during the explosion creates and disperses elements heavier than iron throughout the surrounding space. The shock waves propagating through the stellar material accelerate particles to relativistic speeds, creating cosmic rays that will travel through space for millions of years. Recent observations have revealed supernovae of such extreme power that astronomers have created an entirely new category, hypernovae. These stellar explosions release energies more than 10 times greater than typical supernova, with some events approaching the power output of short gamma-ray bursts. The hypernova that created supernova 1998 BW released energy equivalent to about 50 typical supernova, demonstrating that even among these extreme events, there are gradations of power that push cosmic engineering to its limits. The most powerful hypernovae appear to be associated with the formation of stellar mass black holes, creating a direct connection between the universe's most extreme stellar explosions and the birth of its most efficient gravitational engines. These events represent moments when stellar evolution crosses a threshold, transforming ordinary matter into the exotic conditions found only in the most extreme cosmic environments. But even hypernovae pale in comparison to phenomena that astronomers are only beginning to understand. Enter gamma-ray bursts, cosmic explosions so powerful They represent the second most energetic events in the universe after the Big Bang itself. These brief flashes of the highest energy light known to physics can release more energy in a few seconds than our sun will produce over its entire lifetime. The most powerful gamma-ray burst ever recorded, designated GRB 22109A and dubbed the BOAT for brightest of all time, exemplifies the extreme nature of these cosmic explosions. Located over 2 billion light-years away, this burst was so energetic that it measurably affected Earth's upper atmosphere. The energy released in just the first few seconds exceeded what our entire galaxy produces over several centuries. Gamma-ray bursts demonstrate power through their ability to focus enormous energies into highly collimated jets traveling at 99.9% of the speed of light. These jets punch through the stellar materials surrounding the explosion source, creating beams of radiation so intense they remain visible across billions of light-years of space. The focusing mechanism allows relatively modest energy releases to create the most luminous electromagnetic phenomena in the observable universe. The discovery of gamma-ray burst afterglows has revealed that these events continue releasing energy across the entire electromagnetic spectrum for weeks or months after the initial explosion. X-ray, optical, and radio observations show expanding shockwaves interacting with surrounding material, creating a complex cascade of energy release mechanisms that multiply the total power output of these already extreme events. Long-duration gamma-ray bursts, lasting more than 2 seconds, appear to be associated with the deaths of the most massive stars in the universe. These stellar giants, containing 50 to 100 times the mass of our Sun, represent the upper limit of stellar evolution. When such massive stars collapse, they don't just form neutron stars. They create stellar mass black holes surrounded by rapidly rotating disks of superheated material. The combination of rapid rotation and intense magnetic fields in these newly formed systems creates the perfect conditions for launching relativistic jets. These jets carry away significant fractions of the explosion energy, focusing it into narrow beams that can be detected across cosmic distances. The result is a cosmic lighthouse effect, where the total energy release might be relatively modest, but the focused beam creates the most intense electromagnetic signals in the known universe. Short-duration gamma-ray bursts, lasting less than 2 seconds, reveal an entirely different class of cosmic violence. These events appear to be produced by the collision of ultra-compact stellar remnants, neutron stars, stellar mass black holes, or combinations thereof. When two neutron stars spiral into each other over millions of years, their final merger releases gravitational binding energy equivalent to several percent of their rest mass, converted directly into kinetic energy and electromagnetic radiation. The 2017 detection of gravitational waves from such a merger, designated GW170817, opened an entirely new window into these extreme events. The gravitational wave signal revealed the in-spiral and collision of two neutron stars with exquisite precision, while simultaneous gamma-ray observations captured the electromagnetic signature of the resulting explosion. This multi-messenger observation provided unprecedented insights into how the most compact objects in the universe release energy through gravitational dynamics. These neutron star mergers serve as cosmic forges, where the heaviest elements in the periodic table are created through rapid neutron capture processes. The extreme neutron densities and temperatures achieved during the collision enable nuclear reactions impossible under any other natural conditions. Gold, platinum, uranium, and other elements heavier than iron are synthesized and dispersed into space, seeding future generations of stars and planets with the materials necessary for complex chemistry. But neutron star mergers reveal another aspect of ultimate cosmic power: the ability to create and manipulate the fundamental fabric of space-time itself. When two neutron stars collide, They don't just release electromagnetic energy and create heavy elements. They generate gravitational waves that carry away significant fractions of the merger energy at the speed of light, creating ripples in space-time that can be detected across billions of light years. The power required to generate detectable gravitational waves represents a new category of cosmic energy release. Unlike electromagnetic radiation, which can be absorbed or scattered by intervening matter, gravitational waves propagate freely through space, carrying information about the most violent events in cosmic history directly to our detectors. The energy transported by these space-time distortions represents power channeled through gravity itself, demonstrating how the fundamental forces of nature can serve as conduits for energy on cosmic scales. As we delve deeper into the hierarchy of cosmic power, we encounter objects that push the boundaries of what's physically possible even further. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, represent environments where electromagnetic forces reach strengths comparable to the nuclear forces holding atomic nuclei together. These cosmic magnets demonstrate power through their ability to maintain field strengths that would tear apart ordinary matter at the atomic level. A magnetar's magnetic field contains energy densities so extreme that they can crack the neutron star's crust like an eggshell, releasing seismic waves that propagate around the stellar surface at significant fractions of the speed of light. When these magnetic field lines reconnect and snap, they release bursts of X-ray and gamma-ray radiation that briefly outshine all other sources in their local galactic neighborhood. The most powerful magnetar burst on record released more energy than our Sun has emitted over the past 100,000 years, concentrated into a tenth of a second. This represents power densities that approach the theoretical limits imposed by the fundamental constants of physics, demonstrating how extreme environments can concentrate energy to levels that challenge our understanding of what's possible in nature. Yet even magnetars, with their reality-warping magnetic fields, operate within the confines of known physics. As we push further into the realm of ultimate cosmic power, we encounter phenomena that exist at the very edges of theoretical possibility, where the familiar laws of nature begin to break down, and new forms of physics emerge from the extreme conditions themselves. The journey through cosmic power has revealed a universe far more violent and energetic than our everyday experience suggests. From the steady engines of supermassive black holes to the explosive fury of gamma-ray bursts, we've explored phenomena that operate on energy scales thousands of trillions of times greater than anything humans have ever created or controlled. But our exploration of ultimate power is far from complete. The most mysterious and potentially most powerful forces in the universe operate not through the concentration of energy into compact objects, but through their influence on the largest scales imaginable. We're about to encounter phenomena that don't just release energy, but actively shape the expansion and fate of the universe itself. The forces we've encountered so far operate through mechanisms we can observe, measure, and at least partially understand. But as we venture deeper into the cosmic hierarchy of power, we encounter something far more mysterious and potentially far more influential than any black hole, supernova, or gamma-ray burst. We're about to confront a force so fundamental and so pervasive that it literally determines the fate of everything that exists. Dark energy represents perhaps the most profound mystery in modern cosmology, and quite possibly the most powerful force operating in our universe today. Unlike the concentrated power of black holes or the explosive violence of supernovae, dark energy works quietly and invisibly, but its influence extends across every cubic meter of space that exists. This mysterious force currently drives the accelerated expansion of the entire cosmos, overpowering the gravitational attraction of all matter combined. To understand the staggering scope of dark energy's power, we need to grasp what it's actually accomplishing. Every second that passes, dark energy pushes galaxies farther apart against the combined gravitational pull of hundreds of billions of galaxies. Dark matter structures spanning millions of light years, and all the ordinary matter that fills the cosmic web. The energy required to accelerate the expansion of space itself across the observable universe represents power on scales that dwarf every other phenomenon we've discussed. Current observations suggest that dark energy comprises roughly 68% of the universe's total energy budget. This means that more than 2/3 of all energy in existence takes the form of this mysterious force that we can only detect through its gravitational effects on cosmic expansion. The implications are staggering. Dark energy isn't just another player in the cosmic power game, it's the dominant component of reality itself. What makes dark energy particularly fascinating from a power perspective is how it scales with cosmic expansion. Unlike matter, which becomes more dilute as space expands, dark energy appears to maintain constant density even as the universe grows larger. This means that as space expands, the total amount of dark energy in the universe actually increases. We're dealing with a force that becomes more powerful over time, gradually overwhelming every other form of energy in the cosmos. The accelerating expansion driven by dark energy has profound implications for the ultimate fate of everything we can see. Current projections suggest that this cosmic acceleration will eventually separate galaxy clusters beyond the reach of light itself. In the far future, dark energy will stretch space so rapidly that galaxies beyond our local group will disappear beyond the cosmic horizon, their light redshifted into invisibility by the expansion of space-time. But dark energy's power extends beyond just driving cosmic expansion. Recent theoretical work suggests that this mysterious force might be capable of phenomena that push the boundaries of physics itself. Some models predict that dark energy could undergo phase transitions similar to those that occurred during cosmic inflation, potentially triggering periods of exponential expansion that would dwarf the original inflationary epoch that followed the Big Bang. The mystery deepens when physicists attempt to calculate what dark energy actually is. The most straightforward interpretation suggests it might represent the energy inherent in empty space itself, the quantum vacuum fluctuations that exist even in regions completely devoid of matter and radiation. But when theoretical physicists calculate the expected energy density of quantum vacuum fluctuations, they arrive at values that exceed observations by a factor of 10 to the power of 120. This represents the worst theoretical prediction in the history of physics, highlighting how little we understand about the force that dominates our universe. Alternative theories propose that dark energy might not be a fundamental property of space, but rather a manifestation of modifications to gravity itself on cosmic scales. These models suggest that our understanding of gravitational physics breaks down when applied to the largest structures in the universe, requiring new mathematical frameworks that naturally produce accelerated expansion without invoking mysterious energy components. The power of dark energy becomes even more remarkable when we consider its apparent fine-tuning. If dark energy was slightly stronger, it would have prevented the formation of galaxies and stars by driving expansion so rapidly that matter could never collapse under its own gravity. If it were slightly weaker, the universe might have already begun contracting under the influence of matter and radiation, leading to a big crunch rather than the heat death that current observations predict. This cosmic balancing act suggests that dark energy operates at exactly the right strength to allow for the formation of complex structures, while still dominating the universe's long-term evolution. Whether this represents a fundamental principle of physics or an extraordinary cosmic coincidence remains one of the deepest puzzles in modern science. But dark energy isn't the only mysterious force that might claim the title of most powerful phenomenon in the universe. As we push toward the absolute limits of theoretical physics, we encounter concepts that exist at the very foundations of reality itself. These aren't just powerful objects or events, but fundamental aspects of how space-time, matter, and energy interact at the deepest possible levels. Consider the concept of Planck energy, the natural unit of energy that emerges from the fundamental constants of quantum mechanics, relativity, and gravity. At approximately 2 billion joules, Planck energy might seem modest compared to the cosmic phenomena we've discussed, but this energy scale represents something far more profound than simple magnitude. It marks the boundary where our current understanding of physics completely breaks down. At energies approaching the Planck scale, quantum effects become so strong that they begin to significantly curve space-time itself. The distinction between matter and energy, between particles and fields, between space and time, all become meaningless. We enter a realm where the very concepts we use to describe reality lose their conventional meaning. This isn't just about powerful phenomena, it's about the fundamental limits of physical law itself. The early universe briefly operated at energy scales approaching Planck energies. During the first fleeting moments after the Big Bang, when all of space was smaller than a proton and hotter than anything we can currently imagine. The physics governing these extreme conditions might have produced phenomena that make our most powerful cosmic events seem trivial by comparison. Quantum fluctuations in the primordial vacuum might have created and destroyed entire pocket universes in timeframes measured in Planck times, the smallest meaningful units of temporal measurement. Some theoretical models suggest that the universe might still harbour remnants from this primordial epoch, exotic objects that formed when physics operated under completely different rules. Primordial black holes, if they exist, could demonstrate power through mechanisms we've never observed in nature. These hypothetical objects might have formed when quantum fluctuations in the early universe created density variations so extreme that regions of space collapsed directly into black holes without ever forming stars. Unlike the supermassive black holes we discussed earlier, primordial black holes could span an enormous range of masses, from microscopic objects smaller than atomic nuclei to giants exceeding the mass of entire galaxies. The smallest primordial black holes would have evaporated through Hawking radiation billions of years ago, but their final moments would have produced energy releases that briefly exceeded the power output of entire stars. The largest primordial black holes, if they exist, could dwarf even Ton 618 in their gravitational influence. These hypermassive objects might serve as the seeds around which the first galaxies formed, their gravitational fields shaping cosmic structure during the universe's earliest epochs. The power they wielded during galaxy formation could have determined the large-scale architecture of the cosmos we observe today. But primordial black holes represent just one category of exotic objects that might exist at the extremes of cosmic power. Strange quark stars, if they can form, would demonstrate power through the manipulation of matter at the most fundamental level. These hypothetical objects would be composed not of ordinary protons and neutrons, but of strange quarks in a state that doesn't exist anywhere else in nature. The strange matter that comprises these objects might be more stable than ordinary nuclear matter, potentially triggering a phase transition that could convert entire neutron stars into strange quark stars. This conversion process would release binding energies that exceed nuclear fusion by factors of millions, creating explosions that could outshine gamma-ray bursts. The very existence of strange quark stars would represent a triumph of the strong nuclear force over conventional atomic structure, demonstrating how the fundamental forces of nature can create phenomena that transcend our normal categories of matter and energy. Even more speculative are theoretical objects like white holes, the time-reversed solutions to Einstein's field equations that would represent the ultimate expression of energy creation rather than energy consumption. While black holes absorb everything that crosses their event horizons, white holes would explosively reject all matter and energy, creating fountains of radiation that could dwarf quasars in their luminosity. The theoretical power output of white holes knows no upper limit. These objects could, in principle, create matter and energy from the quantum vacuum itself, violating our normal understanding of conservation laws through mechanisms that exploit the deepest structures of space-time geometry. If white holes exist, they might explain some of the most energetic phenomena we observe, from gamma-ray bursts to the mysterious fast radio bursts that appear and disappear across cosmic distances. The search for these exotic objects pushes observational astronomy to its absolute limits. Current telescopes and detectors operate at the edge of what's technologically possible, hunting for signatures of phenomena that might exist only in the most extreme environments. The recent detection of gravitational waves has opened entirely new windows into cosmic violence, revealing neutron star mergers and black hole collisions that were previously invisible to conventional astronomy. Future observational campaigns will probe even deeper into the cosmic hierarchy of power. The next generation of gravitational wave detectors will be sensitive enough to detect the merger of primordial black holes if they exist. Advanced gamma-ray telescopes will search for the distinctive signatures of strange quark star formation. Radio arrays spanning continents will hunt for the electromagnetic echoes of white hole explosions, if such objects can exist in our universe. Each new observation adds another piece to the puzzle of cosmic power, revealing phenomena that challenge our understanding of what's possible under the laws of physics. The universe continues to surprise us with demonstrations of energy release and matter manipulation that exceed our most ambitious theoretical predictions. As we stand at the current frontier of cosmic exploration, one thing becomes clear. The question of what represents the most powerful thing in the universe doesn't have a simple answer. Power manifests in countless different ways across the cosmic landscape, from the concentrated violence of stellar explosions to the pervasive influence of dark energy, from the reality-warping effects of extreme gravity to the fundamental forces that hold atomic nuclei together. The cosmic power hierarchy we've explored reveals a universe that operates on energy scales that challenge human comprehension. Every category of phenomenon we've examined pushes the boundaries of physics in different ways, demonstrating that ultimate power isn't just about energy release, but about the ability to manipulate the fundamental structures of reality itself. Our journey through cosmic extremes has revealed that we live in a universe where the impossible becomes routine, where the laws of physics are stretched to their breaking points, and where the most powerful forces operate on scales that dwarf human imagination. The story of cosmic power is ultimately the story of how matter, energy, space, and time interact under the most extreme conditions nature can create. And perhaps most remarkably, this exploration of ultimate power has shown us that the universe still holds secrets that lie beyond our current understanding. The most powerful thing in the cosmos might be something we haven't yet discovered, operating through mechanisms we haven't yet imagined, waiting to reveal itself through observations we haven't yet made. The cosmic quest for ultimate power continues, and the next discovery could reshape everything we think we know about the limits of what's possible in our extraordinary universe. But as we push beyond even these theoretical extremes, we encounter something that might represent the ultimate expression of power in our universe, something so fundamental that it operates not just within space-time, but actually creates the very fabric of reality itself. We're about to explore the forces that govern the quantum vacuum, where the distinction between existence and non-existence becomes meaningless. The quantum vacuum represents far more than simple emptiness. Even in regions of space completely devoid of matter and radiation, the uncertainty principle ensures that energy fluctuations constantly bubble in and out of existence. These virtual particles appear and disappear in timeframes so brief they exist below the threshold of direct measurement. Yet their cumulative effects shape the behavior of everything we can observe. Recent calculations suggest that the energy density of quantum vacuum fluctuations might exceed the energy contained in all visible matter and radiation by factors that beg a description. If these theoretical predictions prove correct, then every cubic centimetre of apparently empty space contains enough latent energy to power entire civilizations. The vacuum itself becomes the ultimate reservoir of cosmic power, dwarfing even dark energy in its potential influence. But here's where quantum vacuum energy becomes truly mind-bending. Unlike every other form of power we've discussed, vacuum energy doesn't just exist in specific locations or operate through particular mechanisms. It permeates every point in space simultaneously, creating a background energy density that exists everywhere and everywhen. This isn't power that gets released during dramatic cosmic events. It's power that continuously exists as the fundamental substrate of reality itself. The implications stretch beyond physics into philosophy. If vacuum energy represents the true foundation of cosmic power, then everything we've explored, from supermassive black holes to gamma-ray bursts, becomes merely surface phenomena, riding atop an ocean of energy so vast it defies quantification. The most powerful explosions in cosmic history would represent tiny perturbations in this underlying energy field, like waves on an infinite ocean. Yet measuring and harnessing vacuum energy remains beyond our current capabilities. The same quantum mechanical principles that predict its existence also suggest that extracting useful work from vacuum fluctuations might violate fundamental conservation laws. We're dealing with a form of power that might be infinitely abundant, yet eternally inaccessible. The ultimate cosmic tease that promises unlimited energy while remaining forever out of reach. This brings us to perhaps the most profound question in our exploration of cosmic power. As we've journeyed from stellar explosions to exotic matter, from dark energy to quantum vacuum fluctuations, we've encountered phenomena that operate across every conceivable scale of space and time. But which of these truly deserves the title of most powerful thing in the universe? The answer depends entirely on how we define power itself. If we measure power by immediate energy release, gamma-ray bursts claim the crown with their ability to outshine entire galaxies in seconds. If we consider sustained energy output, quasars demonstrate unmatched efficiency in converting matter to radiation across millions of years. If we think about gravitational influence, supermassive black holes shape the evolution of galaxies across cosmic time. But if we define power by fundamental importance to the structure of reality, dark energy emerges as the clear winner. This mysterious force doesn't just influence individual objects or events, it determines the ultimate fate of everything that exists. Dark energy will eventually separate galaxies beyond the reach of light, leaving future civilizations in cosmic isolation as space itself expands faster than information can travel. The truly remarkable aspect of dark energy's power lies in its subtlety. While gamma-ray bursts announce themselves with spectacular displays of electromagnetic radiation, dark energy works silently and invisibly. Yet its influence accumulates over cosmic timescales, gradually overwhelming every other force in the universe. In the far future, when all the stars have died and all the black holes have evaporated, dark energy will still be driving space to expand at ever-increasing rates. This cosmic acceleration reveals something profound about the nature of power in our universe. The most influential forces aren't always the most dramatic ones. Sometimes ultimate power operates through patience and persistence rather than spectacular displays of energy. Dark energy demonstrates that true cosmic dominance comes not from brief moments of extreme violence, but from the ability to shape reality across the entire history of the universe. Yet even dark energy might not represent the final word in cosmic power. As our understanding of physics continues to evolve, we're discovering that the universe operates according to principles we're only beginning to comprehend. The recent detection of gravitational waves has revealed entirely new categories of cosmic violence, while observations of the cosmic microwave background suggest that inflation, the exponential expansion of space during the universe's first moments, might have involved energy densities that exceeded anything we've discussed. Cosmic inflation represents a form of power so extreme that it literally created the observable universe itself. During a period lasting less than a trillionth of a trillionth of a trillionth of a second, space expanded by factors exceeding 10 to the 30th power. The energy driving this expansion stretched quantum fluctuations smaller than atomic nuclei into structures spanning billions of light years, seeding the density variations that would eventually grow into galaxies and galaxy clusters. The inflationary epoch demonstrates power through the manipulation of space-time geometry itself. Unlike objects that release energy through nuclear reactions or gravitational accretion, inflation operated by borrowing energy from the gravitational field and using it to drive exponential expansion. This process created more energy than it consumed, essentially manufacturing the matter and radiation that fill the universe today from the quantum vacuum itself. If inflation represents the ultimate expression of cosmic power, then the most powerful thing in the universe isn't an object at all, but a process, a mechanism that can create entire universes from quantum fluctuations, transforming microscopic uncertainties into macroscopic realities. The energy scales involved in inflation approach the theoretical Planck energy, where quantum mechanics and general relativity merge into a unified description of spacetime at its most fundamental level. But inflation raises profound questions about the nature of cosmic power itself. If physical processes can create universes from quantum vacuum fluctuations, what prevents this from happening continuously? Some theoretical models suggest that inflation might be an eternal process, constantly creating new regions of space that expand into independent universes. This eternal inflation scenario would make our observable universe just one bubble in an infinite multiverse, with new cosmic domains being born from vacuum energy fluctuations throughout eternity. The implications are staggering. If eternal inflation operates as these models suggest, then the most powerful process in existence is one that creates infinite numbers of universes, each with its own physical laws, fundamental constants, and cosmic evolution. The power to generate not just matter and energy, but entire realities with their own space and time dimensions represents the ultimate expression of creative force. This perspective transforms our understanding of cosmic power from a question about the most energetic objects to a recognition that the universe itself might be the product of the most powerful process imaginable. Every galaxy, every star, every planet, every atom exists because inflation borrowed energy from the gravitational field and used it to create space, time, matter, and radiation from quantum nothingness. Yet even eternal inflation might not represent the deepest level of cosmic power. Recent developments in theoretical physics suggest that reality itself might emerge from even more fundamental processes operating in mathematical spaces that transcend our normal concepts of energy, matter, and space-time. These theories propose that what we perceive as the physical universe represents just one possible manifestation of underlying mathematical structures that exist independently of any particular cosmic domain. From this perspective, the most powerful thing in the universe might not be a physical process at all, but the mathematical principles that determine which realities can exist and how they evolve over time. The laws of physics themselves become expressions of deeper mathematical truths that operate beyond the boundaries of any particular universe or multiverse. This recognition brings us to a profound realization about the nature of cosmic power. Throughout our exploration, we've encountered phenomena that push the boundaries of physics to their absolute limits. From black holes that warp space-time to gamma-ray bursts that release more energy than entire galaxies, we've seen how matter and energy can achieve extremes that challenge human comprehension. But perhaps the most powerful thing in the universe is the framework of natural laws that makes all of these phenomena possible. The mathematical relationships that govern how matter and energy interact, how space-time responds to mass and energy, how quantum fields give rise to particles and forces. These underlying principles don't just describe cosmic power, they define what power can mean in our universe. The constants of nature that determine the strength of fundamental forces, the masses of particles, and the curvature of space-time represent a form of power that transcends any individual object or event. These constants shape every interaction that has ever occurred or ever will occur throughout cosmic history. They determine whether stars can form, whether atoms can exist, whether complexity can emerge from simplicity. If these fundamental constants had slightly different values, none of the powerful phenomena we've explored could exist. Stars wouldn't ignite, black holes couldn't form, and the universe would remain a cold, dark expanse of elementary particles. The apparent fine-tuning of these constants suggests that the most powerful thing in the universe might be whatever process or principle determined their specific values. This brings us full circle to questions that extend beyond physics into the deepest mysteries of existence itself. Why do the laws of physics take the particular form they do? Why do the fundamental constants have the specific values that allow for complex structures and processes? Why does the universe contain mechanisms capable of creating power on the scales we've explored? These questions remind us that our journey through cosmic power has revealed not just the most energetic phenomena in nature, but the incredible richness and complexity that emerges when matter, energy, space, and time interact according to mathematical principles of breathtaking elegance and precision. As we stand at the current frontier of human knowledge, looking out at a universe filled with black holes that outmass billions of suns, explosions that outshine entire galaxies, and mysterious forces that determine the fate of everything that exists, we're confronted with a humbling truth. The most powerful thing in the universe might be the creative potential inherent in reality itself. The capacity for simple mathematical relationships to give rise to phenomena of such complexity and beauty that they inspire wonder across cosmic distances and geological timescales. Every photon of light that has travelled billions of years to reach our telescopes, every gravitational wave that carries information about cosmic collisions across intergalactic space, every neutrino that passes through our planet after escaping from stellar cores represents a message from the universe about the incredible power and creativity embedded in the fundamental structure of reality. The cosmic power we've explored isn't separate from us. It's the same creative force that assembled the atoms in our bodies from stellar nuclear reactions that shaped the galaxy we call home, through gravitational interactions spanning billions of years that created the conditions necessary for consciousness to emerge and contemplate its own cosmic origins. In this sense, the most powerful thing in the universe might be the process by which unconscious matter and energy organize themselves into systems complex enough to understand power itself. The emergence of intelligence represents the universe becoming aware of its own creative potential, developing the capacity to study and appreciate the very forces that brought it into existence. This realization transforms our exploration of cosmic power from an academic exercise into a profound recognition of our connection to the most fundamental processes in nature. We are not separate observers of cosmic violence and creativity. We are products of these same forces, temporary concentrations of matter and energy that have achieved the remarkable ability to contemplate the cosmos that created us. The journey through ultimate cosmic power reveals a universe that operates on scales of energy and creativity that challenge every assumption about what's possible in nature. From quantum vacuum fluctuations to eternal inflation, from gamma-ray bursts to dark energy, we've encountered phenomena that push the boundaries of physics while demonstrating the incredible richness that emerges from relatively simple mathematical principles. As we continue to probe deeper into the mysteries of cosmic power, new discoveries await that will undoubtedly challenge and expand our understanding even further. The universe continues to surprise us with demonstrations of energy release and matter manipulation that exceed our most ambitious theoretical predictions, reminding us that the story of cosmic power is far from complete. The most powerful thing in the universe remains, in many ways, an open question. But our exploration has revealed something perhaps even more remarkable, a cosmos so rich in creative potential that the question itself opens doorways to understanding that extend from the smallest scales of quantum mechanics to the largest structures of space-time itself. In our quest to understand ultimate cosmic power, we've journeyed through realms where individual objects release more energy than entire civilizations could harness across millennia. But there's another category of cosmic phenomena that demonstrates power through sheer magnetic dominance, where electromagnetic forces reach strengths that would atomize ordinary matter from hundreds of miles away. Welcome to the realm of Magnetars, the universe's most magnetic objects, where stellar remnants no larger than cities generate fields trillions of times stronger than anything we experience on Earth. These cosmic magnets represent what happens when the laws of electromagnetism are pushed to their absolute breaking point, creating environments so extreme that atoms themselves begin to behave in ways that defy our everyday understanding of matter. To comprehend the power of magnetars, we need to first understand their origin story. These objects begin their lives as massive stars, perhaps 20 to 40 times more massive than our Sun, burning through their nuclear fuel in cosmic fast-forward. When such giants exhaust their ability to sustain fusion reactions, they undergo the same core collapse we explored with Supernova, but with a crucial difference. The rotating magnetic field of the original star gets compressed along with everything else. Imagine taking Earth's magnetic field and squeezing it into a sphere just 20 kilometers across, while simultaneously spinning it hundreds of times per second. The resulting magnetic field strength approaches limits that theoretical physics suggests might be impossible to exceed. We're talking about field strengths of 10 to the 15th Gauss, roughly 1 trillion times stronger than the most powerful magnetic fields humans have ever created in laboratory conditions. These magnetic fields contain energy densities so extreme that they literally crack the neutron star's crust like an eggshell. The solid surface of these objects, composed of matter so dense that a teaspoon would weigh as much as Mount Everest, fractures under the immense magnetic stress. When this happens, the magnetic field lines snap and reconnect in violent processes that release more energy than our Sun produces over thousands of years, concentrated into bursts lasting mere seconds. The 2004 outburst from Magnetar SGR 1806-20 demonstrated the terrifying power of these magnetic monsters in ways that affected our entire solar system. Located 50,000 light-years away, this brief magnetic eruption saturated every gamma-ray detector on and around Earth, temporarily blinding our most sensitive instruments. The energy release was so intense that it measurably compressed Earth's magnetic field from a distance greater than the diameter of our galaxy. To put this in perspective, imagine a city-sized object 50,000 light-years away having a detectable effect on Earth's magnetic environment. This single burst released more energy than our Sun will produce over the next 100,000 years, all originating from magnetic processes in an object smaller than most metropolitan areas. The power density achieved during this event approached the theoretical limits imposed by the fundamental constants of physics. But magnetars demonstrate power through more than just their explosive outbursts. These objects maintain their extreme magnetic fields for thousands of years, slowly dissipating the enormous energies stored in their twisted field lines. The steady X-ray and gamma-ray emission from magnetars represents a form of controlled power release that exceeds the luminosity of most ordinary stars, sustained not by nuclear fusion, but purely by magnetic field decay. The recent reactivation of Magnetar XTJ1810-197 has provided unprecedented insights into how these cosmic dynamos operate. After remaining dormant for over a decade, this magnetar suddenly awakened with a series of powerful bursts that revealed the complex interplay between magnetic fields, rotation, and matter under extreme conditions. Radio telescopes detected rapid changes in the magnetar's emission properties, suggesting that the magnetic field structure was undergoing dramatic reorganization in real time. These observations reveal that magnetars aren't static objects, but dynamic systems where magnetic forces constantly reshape the stellar surface and surrounding environment. The power involved in these magnetic restructuring events demonstrates how electromagnetic forces can achieve energies comparable to gravitational collapse, but operating through completely different physical mechanisms. The magnetic fields of magnetars are so intense that they affect the quantum vacuum itself, at field strengths exceeding the so-called critical field of quantum electrodynamics. Virtual particle pairs become real, creating matter and antimatter from pure electromagnetic energy. This process, known as magnetic pair creation, transforms magnetars into cosmic particle accelerators that generate high-energy radiation through purely quantum mechanical effects. Near the surface of the most powerful magnetars, the magnetic field becomes strong enough to distort atomic structure itself. Atoms stretched into needle-like shapes aligned with field lines, while the energy levels that normally define chemical properties shift dramatically. In these extreme magnetic environments, ordinary matter behaves according to rules we never encounter in terrestrial physics, demonstrating how electromagnetic forces can reshape reality at the most fundamental level. Yet even as magnetars represent the pinnacle of magnetic power in our universe, they face competition from phenomena that operate through entirely different mechanisms. As we continue our exploration of cosmic extremes, we encounter objects that demonstrate power not through magnetic dominance, but through their ability to maintain the most efficient energy conversion processes known to physics across millions of years. Quasars stand as cosmic lighthouses, visible across billions of light years, powered by supermassive black holes that have perfected the art of converting matter into energy with unprecedented efficiency. These objects represent the marriage of extreme gravity and electromagnetic processes, creating some of the most luminous phenomena in the observable universe. The record-holding quasar, designated J0529-4351, exemplifies the staggering power outputs these objects can achieve. Located over 12 billion light-years away, this cosmic beacon shines with the luminosity of 500 trillion suns. To put this in perspective, if this single object were placed at the center of our galaxy, it would outshine all 400 billion stars, combined by factors of thousands. What makes quasars particularly impressive from a power perspective is their incredible efficiency at energy conversion. While nuclear fusion in stellar cores converts roughly 0.7% of mass into energy, the accretion processes around supermassive black holes can convert up to 40% of infalling matter directly into radiation. This represents the most efficient energy production mechanism known to physics, exceeded only by the complete annihilation of matter and antimatter. The supermassive black hole powering J0529-4351 consumes matter equivalent to one entire sun every single day, converting significant fractions of this material into electromagnetic radiation across the entire spectrum from radio waves to gamma rays. The accretion disk surrounding this monster reaches temperatures of millions of degrees, creating conditions where atomic nuclei are stripped of their electrons, and matter exists in plasma states that don't occur naturally anywhere else in the universe. But quasars demonstrate power through more than just their prodigious energy output. These objects launch jets of plasma at velocities approaching the speed of light, carrying energy and magnetic fields across distances measured in millions of light-years. The jets from the most powerful quasars maintain their coherent structure across intergalactic space, affecting the temperature and magnetic properties of the cosmic web itself. Recent observations have revealed quasar jets extending across distances so vast they challenge our understanding of how electromagnetic processes can maintain coherence over such scales. The jet from Quasar 3c, 273, spans over 200,000 light-years, remaining collimated despite travelling through regions of space filled with galaxy clusters and dark matter structures that should disrupt such narrow beams. These jets represent one of nature's most efficient energy transport mechanisms, carrying power generated in regions smaller than our solar system, across distances comparable to the separation between galaxies. The magnetic fields threading through these jets channel energy with minimal losses, creating cosmic power transmission lines that operate on scales humans can barely comprehend. The longevity of quasar activity adds another dimension to their claim as cosmic powerhouses. While gamma-ray bursts release enormous energies over seconds and supernovae operate over months, quasars can maintain their extreme luminosities for millions of years. The most active quasars represent steady-state cosmic engines that have been converting matter into energy at prodigious rates since the universe was less than 1 billion years old. This sustained power output reveals something profound about the physics operating in these extreme environments. The accretion disks around supermassive black holes achieve a delicate balance between gravitational infall, magnetic field pressure, and radiation pressure that allows them to maintain stable energy production across geological timescales. These systems demonstrate how gravitational and electromagnetic forces can work together to create the most luminous objects in the cosmic inventory. But quasars also reveal the interconnected nature of cosmic power hierarchies. The supermassive black holes that power these objects didn't emerge from nothing. They represent the end products of cosmic evolution spanning billions of years. Some may have grown from smaller seed black holes formed by the first generation of stars, while others might trace their origins to direct collapse of primordial gas clouds in the early universe. The feedback mechanisms between quasars and their host galaxies demonstrate how cosmic power operates across multiple scales simultaneously. The energy output from active galactic nuclei can regulate star formation across entire galaxies, determining the rate at which new stars are born and influencing the chemical evolution of galactic environments. In this sense, quasars don't just demonstrate individual power, they serve as cosmic regulators that shape the development of structure throughout the universe. Recent discoveries have revealed quasars operating at redshifts corresponding to when the universe was less than 700 million years old, challenging our understanding of how such massive black holes could have formed so early in cosmic history. These primordial quasars required mechanisms for rapid black hole growth that pushed accretion processes beyond the theoretical limits imposed by radiation pressure. The existence of such early quasars suggests that the universe's first billion years witnessed episodes of black hole growth and energy release that exceeded anything we observe in the contemporary cosmos. These ancient powerhouses may have played crucial roles in reionizing the hydrogen that filled space after recombination, transforming the universe from an opaque fog into the transparent medium that allows light to travel freely across cosmic distances. As we delve deeper into the cosmic power hierarchy, we encounter phenomena that push beyond the steady engines of quasars into realms where energy release occurs through mechanisms so exotic they challenge the boundaries between theoretical physics and observable reality. We're about to explore objects that exist at the very limits of what the laws of physics allow, where matter and energy interact in ways that stretch our understanding of what's possible in nature. Strange quark stars represent one of the most exotic possibilities in the cosmic bestiary, objects where the familiar protons and neutrons that compose ordinary matter give way to configurations of quarks that might be more stable than atomic nuclei themselves. If these hypothetical objects exist, they would demonstrate power through the conversion of ordinary nuclear matter into strange matter, releasing binding energies that exceed nuclear fusion by factors of millions. The theoretical framework for strange quark stars emerges from our understanding of quantum chromodynamics, the theory that describes how quarks interact through the strong nuclear force. Under the extreme pressures found in neutron star cores, the individual protons and neutrons might dissolve entirely, allowing their constituent quarks to rearrange into more stable configurations that include strange quarks alongside the up and down quarks found in ordinary matter. This phase transition from nuclear matter to strange quark matter would release enormous amounts of binding energy, potentially triggering explosions that could outshine gamma-ray bursts. The conversion process might propagate through neutron star material like a nuclear chain reaction, transforming entire stellar remnants into forms of matter that don't exist anywhere else in the contemporary universe. Recent observations of unusually massive neutron stars have renewed interest in strange quark star possibilities. Objects like PSR J 0348, 0432, with masses approaching twice that of our Sun compressed into 20-kilometer spheres, test the theoretical limits of how much matter-neutron degeneracy pressure can support. If strange quark matter proves more stable than neutron matter at these extreme densities, then the most massive neutron stars might actually be strange quark stars in disguise. The implications for cosmic power are staggering. Strange quark stars would represent the most efficient binding energy release mechanism in nature, exceeding even the matter-antimatter annihilation that powers the most exotic theoretical rockets. A single neutron star converting to a strange quark star could release energy equivalent to hundreds of supernovae, creating electromagnetic signals visible across billions of light years. But strange quark stars face competition from even more exotic possibilities that exist at the very edges of theoretical physics. White holes, the time-reversed solutions to Einstein's field equations, would represent the ultimate expression of energy creation rather than energy consumption. While black holes absorb everything that crosses their event horizons, white holes would explosively reject all matter and energy, creating fountains of radiation that could dwarf quasars in their luminosity. The theoretical power output of white holes knows no upper limit. These objects could, in principle, create matter and energy from the quantum vacuum itself, violating our normal understanding of conservation laws through mechanisms that exploit the deepest structures of space-time geometry. If white holes exist, they might explain some of the most energetic phenomena we observe, from gamma-ray bursts to the mysterious, fast radio bursts that appear and disappear across cosmic distances. The search for white hole signatures represents one of the most speculative frontiers in observational astronomy. These objects would produce electromagnetic signatures unlike anything generated by conventional astrophysical processes, creating bursts of radiation that emerge without warning from apparently empty regions of space. The challenge lies in distinguishing genuine white hole emissions from other exotic phenomena that might mimic their observational signatures. Recent theoretical work has suggested that white holes might be connected to black holes through wormhole geometries that exist entirely within the structure of space-time itself. These Einstein-Rosen bridges could provide conduits through which matter and energy absorbed by black holes in one region of the universe emerge as white hole emissions in completely different cosmic domains. If such connections exist, they would represent the ultimate demonstration of cosmic power, mechanisms that can transport matter and energy across arbitrary distances through shortcuts in space-time itself. The energy required to maintain stable wormhole geometries approaches the Planck scale, where quantum effects become strong enough to significantly modify the curvature of space-time. Planck scale phenomena represent the absolute frontier of cosmic power, the realm where energy densities become so extreme that our current understanding of physics completely breaks down. At these energy scales, roughly 2 billion joules concentrated in volumes smaller than atomic nuclear, quantum mechanics and general relativity merge into unified descriptions of space-time that we're only beginning to comprehend. The early universe briefly operated at Planck-scale energies during the first moments after the Big Bang, when all of space was smaller than a proton and temperatures exceeded 10 to the 32nd power Kelvin. The physics governing these extreme conditions might have produced phenomena that make our most powerful cosmic events seem trivial by comparison. Quantum fluctuations in the primordial vacuum might have created and destroyed entire pocket universes in timeframes measured in Planck times, the smallest meaningful units of temporal measurement at roughly 10 to the minus 43rd power seconds. These virtual universes would have contained energies exceeding anything we've discussed, existing in mathematical spaces that transcend our normal concepts of matter, energy, and space-time. The possibility that our observable universe emerged from just such a quantum fluctuation suggests that the most powerful thing in existence might be the creative potential inherent in the quantum vacuum itself. The capacity for empty space to spontaneously generate matter, energy, and space-time through mechanisms that operate entirely outside our normal understanding of causality and conservation laws. Recent developments in quantum field theory suggest that vacuum energy might represent an inexhaustible reservoir of cosmic power, with energy densities that exceed the mass energy of all visible matter by factors that approach infinity. If theoretical calculations prove correct, then every cubic centimeter of apparently empty space contains enough latent energy to power entire galactic civilizations for billions of years. But accessing this vacuum energy remains beyond our current technological capabilities and might be forbidden by fundamental conservation laws that we're only beginning to understand. We're dealing with a form of power that might be infinitely abundant, yet eternally inaccessible. The ultimate cosmic paradox that promises unlimited energy while remaining forever out of reach. This brings us to a profound recognition about the nature of cosmic power itself. Throughout our journey, we've encountered phenomena that operate across every conceivable scale of space, time, and energy. From the electromagnetic dominance of magnetars to the gravitational efficiency of quasars, from the exotic matter transitions in strange quark stars to the quantum creativity of vacuum fluctuations, we've explored a universe where power manifests in countless different forms. Each category of cosmic phenomenon demonstrates power through fundamentally different mechanisms, yet all operate according to the same underlying mathematical principles that govern how matter, energy, space, and time interact. The laws of physics that describe Magnetar outbursts also govern quasar jets, while the quantum mechanics that might create strange quark stars operates according to the same principles that could enable white hole formation. This unity, amid diversity, reveals something remarkable about the cosmos we inhabit. Despite the incredible variety of powerful phenomena we observe, they all emerge from relatively simple mathematical relationships that connect the behavior of matter and energy across scales spanning dozens of orders of magnitude. The same quantum field theory that describes virtual particle creation in the vacuum also explains how magnetars generate their extreme magnetic fields. The cosmic power hierarchy we've explored demonstrates that the universe operates as a unified system where phenomena at different scales influence and constrain each other through mechanisms we're only beginning to understand. The dark energy that drives cosmic expansion affects the formation of the galaxy clusters that host the most powerful quasars, while the feedback from those quasars influences the rate at which new stars form and eventually explode as supernovae. This interconnectedness suggests that asking for the single most powerful thing in the universe might be approaching the question from the wrong perspective. Instead of seeking individual champions in different categories of cosmic violence, we might need to recognize that ultimate power emerges from the interactions between all these phenomena operating simultaneously across the cosmic landscape. The universe reveals itself as a vast engine of creativity and destruction, where matter and energy constantly transform themselves through processes that push the boundaries of what physics allows. From quantum vacuum fluctuations to galactic-scale magnetic fields, from stellar core collapse to the expansion of space-time itself, we live in a cosmos where power operates on scales that challenge human comprehension, while following mathematical principles of breathtaking elegance and precision. As we continue to probe deeper into these cosmic mysteries, new discoveries await that will undoubtedly challenge and expand our understanding even further. The recent detection of gravitational waves has already revealed entirely new categories of cosmic violence, while observations of the cosmic microwave background continue to provide insights into the extreme energies that shaped our universe during its earliest moments. The story of cosmic power remains far from complete, but our exploration has revealed a universe so rich in creative potential that each new discovery opens doorways to understanding that extend from the quantum realm to the largest structures of space-time itself. In this cosmic theatre of ultimate forces, we find ourselves not as passive observers, but as products of the same creative processes we seek to understand, temporary arrangements of matter and energy that have achieved the remarkable ability to contemplate the very forces that brought us into existence. The question becomes even more profound when we consider that the universe might harbour forms of power so exotic they exist at the very boundaries of what mathematics allows. In the deepest reaches of theoretical physics, scientists have identified energy scales where our familiar concepts of space, time, matter, and energy lose all meaning. Welcome to the realm of Planck energy, where roughly 2 billion joules become concentrated into volumes smaller than the nucleus of an atom. This might seem modest compared to the cosmic phenomena we've explored, but Planck energy represents something far more fundamental than simple magnitude. It marks the absolute boundary where quantum mechanics and general relativity collide, creating conditions so extreme that the very fabric of reality begins to dissolve. At energies approaching the Planck scale, quantum effects become strong enough to curve space-time itself. The distinction between particles and fields, between matter and energy, between cause and effect, all become meaningless. We enter a realm where the universe operates according to rules we can barely imagine, let alone observe directly. The early cosmos briefly operated at these unimaginable energy densities during the first fleeting moments after the Big Bang. In timeframes measured in Planck units, roughly 10 to the minus 43rd power seconds, the entire observable universe existed in a state smaller than a proton, yet containing energies that dwarf every phenomenon we've discussed combined. During these primordial moments, quantum fluctuations in spacetime itself might have created and destroyed entire pocket universes in intervals so brief they exist below the threshold of measurement. Virtual realities popping in and out of existence, each containing the potential energy equivalent of billions of galaxies, operating according to physical laws that transcend our current understanding of what's possible. Recent theoretical developments suggest that these Planck-scale processes might still be operating throughout the universe, hidden beneath the surface of what we perceive as empty space. The quantum vacuum, that seemingly quiet backdrop against which all cosmic drama unfolds, might actually be seething with creative energies that make our most violent stellar explosions seem like gentle whispers. Calculations in quantum field theory predict that vacuum energy fluctuations could contain power densities exceeding the mass energy of all visible matter by factors approaching infinity. Every cubic centimeter of apparently empty space might harbor enough latent energy to power entire civilizations across cosmic timescales. We're potentially surrounded by an ocean of power so vast it defies every attempt at quantification. But accessing this vacuum energy remains tantalizingly beyond our reach. The same quantum mechanical principles that predict its existence also suggest that extracting useful work from these fluctuations might violate fundamental conservation laws. We find ourselves contemplating the ultimate cosmic paradox: unlimited power that might be forever inaccessible. This brings us face to face with perhaps the most disturbing possibility in our exploration of ultimate cosmic forces. What if the most powerful thing in the universe isn't an object or phenomenon we can observe, but rather the creative potential embedded in reality itself? The capacity for existence to generate complexity, consciousness, and wonder from mathematical principles operating at scales we can barely comprehend. The journey through cosmic power reveals something extraordinary about our place in this vast hierarchy of forces. Every atom in your body was forged in stellar cores, operating at temperatures exceeding billions of degrees. The calcium in your bones was created during supernova explosions that briefly outshone entire galaxies. The iron in your blood carries the signature of cosmic violence that occurred billions of years before Earth existed. You are not separate from the cosmic power we've explored. You are made of it. The same nuclear forces that drive stellar fusion operates within every cell of your body. The electromagnetic forces that accelerate particles in Magnetar magnetic fields enable the chemical reactions that sustain your thoughts. The gravitational waves that ripple through space-time from distant black hole collisions pass through your body every moment of every day. This realization transforms our understanding of cosmic power from an abstract scientific concept into a deeply personal recognition of our connection to the universe's most fundamental creative processes. We're not observers of cosmic violence, we're products of it, temporary arrangements of stellar debris that have achieved the remarkable ability to contemplate the very forces that created us. The power hierarchy we've explored extends from the quantum realm to the largest structures in space-time, revealing a cosmos where creativity and destruction operate as complementary aspects of the same underlying processes. The gamma-ray bursts that represent the universe's most violent explosions also forge the heavy elements necessary for planetary formation. The supermassive black holes that devour entire solar systems also regulate galaxy formation across cosmic history. This duality suggests that ultimate power in our universe isn't about destruction or creation alone, but about the capacity to transform one form of organization into another. The most powerful phenomena we've encountered share this common thread. They don't just release energy, they restructure reality itself, converting matter into energy, space into time, simplicity into complexity. Dark energy exemplifies this transformative power on the largest possible scales. This mysterious force doesn't just drive cosmic expansion, it actively shapes the future of everything that exists. In the far future, when all the stars have died and all the black holes have evaporated through Hawking radiation, dark energy will still be operating, stretching space at accelerating rates until galaxies disappear beyond the cosmic horizon. The patient, inexorable power of dark energy reveals something profound about the nature of ultimate cosmic forces. Sometimes, the most influential power operates not through spectacular displays of violence, but through subtle, persistent effects that accumulate across the entire history of the universe. True cosmic dominance comes not from brief moments of extreme energy release, but from the ability to determine the fundamental structure of reality across all of space and time. Yet even dark energy operates within a framework of natural laws that might themselves represent the deepest expression of cosmic power. The mathematical relationships that govern how matter and energy interact, how space-time responds to mass and energy, how quantum fields give rise to particles and forces. These underlying principles don't just describe cosmic phenomena, they define what power can mean in our universe. The constants of nature that determine the strength of fundamental forces represent a form of power that transcends any individual object or event. The fine structure constant that governs electromagnetic interactions, the gravitational constant that determines how matter curves space-time, the Planck constant that sets the scale of quantum effects. These numbers shape every interaction that has ever occurred or ever will occur throughout cosmic history. If these fundamental constants had slightly different values, none of the powerful phenomena we've explored could exist. Stars wouldn't ignite, atoms couldn't form stable configurations, and the universe would remain a cold, dark expanse of elementary particles. The apparent fine-tuning of these constants suggests that the most powerful thing in the universe might be whatever process or principle determined their specific values. This recognition leads us to questions that extend beyond physics into the deepest mysteries of existence itself. Why do the laws of physics take the particular mathematical form they do? Why do the fundamental constants have the specific values that allow for the incredible diversity of cosmic phenomena we observe? Why does the universe contain mechanisms capable of creating power on the scales we've explored? Recent discoveries in cosmology and quantum physics hint that our observable universe might be just one domain in a vast multiverse, where different regions operate according to different physical laws and fundamental constants. In this cosmic landscape, universes with suitable conditions for complex phenomena, like stars, galaxies, and life, represent tiny islands of habitability in an ocean of sterile mathematical possibilities. If this multiverse scenario proves correct, then the most powerful force in existence might be the mechanism that generates this infinite variety of cosmic domains, each testing different combinations of physical laws and constants. The process that creates not just matter and energy, but the very mathematical frameworks within which matter and energy can interact. This perspective transforms our exploration of cosmic power into something far more profound than a catalogue of energetic phenomena. We're not just studying the most powerful objects in our universe, we're glimpsing the creative processes that generate reality itself across scales that extend from quantum fluctuations to infinite multiverses. The power we've encountered operates through mechanisms so fundamental they challenge our basic concepts of existence and causality. From magnetars that twist space-time through electromagnetic dominance to gamma-ray bursts that announce stellar death across billions of light-years, from quasars that convert matter into energy with unprecedented efficiency to dark energy that reshapes the cosmos across all of space and time. Each phenomenon reveals different aspects of how the universe organizes and reorganizes itself through processes that push physical laws to their absolute limits. The mathematical elegance underlying these extreme conditions suggests that ultimate power emerges not from chaos or random violence, but from the precise application of natural principles operating under conditions we can barely imagine. As we stand at the current frontier of cosmic exploration, our instruments detecting gravitational waves from colliding black holes, gamma rays from magnetar outbursts, and the subtle signatures of dark energy in the cosmic microwave background. We find ourselves participants in the universe's ongoing project of self-discovery. Every observation adds another piece to our understanding of how power operates across the cosmic hierarchy. Every theoretical breakthrough reveals new possibilities for phenomena that might exist at energy scales we haven't yet learned to probe. The story of cosmic power continues to unfold as the universe itself evolves, creating new demonstrations of creative force that challenge and expand our comprehension of what's possible. The question of what represents the most powerful thing in the universe doesn't have a simple answer, because power manifests differently across every scale of space, time, and energy. The concentrated violence of gamma-ray bursts, the sustained luminosity of quasars, the magnetic dominance of magnetars, the gravitational efficiency of supermassive black holes, the mysterious influence of dark energy, the creative potential of quantum vacuum fluctuations. Each represents ultimate power expressed through fundamentally different mechanisms, yet all emerge from the same underlying mathematical principles that govern how reality organizes itself. The cosmic power hierarchy reveals a universe where the impossible becomes routine, where the laws of physics are stretched to their breaking points, and where the most fundamental forces operate on scales that dwarf human imagination. Perhaps the most remarkable discovery in our exploration is that we live in a cosmos specifically structured to generate phenomena of such incredible power and complexity. The fine-tuning of physical constants, the mathematical elegance of natural laws, the creative potential embedded in quantum vacuum fluctuations all suggest that our universe possesses an inherent tendency toward the development of increasingly sophisticated expressions of organized energy. In this context, the emergence of consciousness represents the universe's most remarkable achievement, the development of matter and energy configurations complex enough to contemplate their own cosmic origins. Through our exploration of ultimate power, we're not just studying astrophysical phenomena, we're participating in the cosmos' ongoing project of understanding itself. The power we've encountered connects us intimately to the deepest creative processes in nature. Every thought you think emerges from neural networks powered by the same electromagnetic forces that accelerate particles in Magnetar magnetic fields. Every breath you take processes oxygen forged in stellar cores through nuclear reactions that release energies approaching those found in supernova explosions. We are the universe becoming conscious of its own power, matter learning to appreciate the forces that brought it into existence. In contemplating cosmic extremes, we're engaging with the most fundamental aspects of reality while recognizing our profound connection to the creative processes that continue shaping the cosmos around us. The journey through ultimate cosmic power reveals a universe far stranger, more violent, and more creative than our everyday experience suggests. From stellar explosions that outshine entire galaxies to mysterious forces that determine the fate of everything that exists, we've explored phenomena that challenge every assumption about the limits of what's possible in nature. As our understanding continues to evolve, new discoveries await that will undoubtedly reveal even more extreme expressions of cosmic creativity. The universe continues to surprise us with demonstrations of power that exceed our most ambitious theoretical predictions, reminding us that the story of ultimate forces is far from complete. In the vast cosmic theatre where magnetars generate reality-warping magnetic fields, where gamma-ray bursts announce stellar death across billions of light-years, where dark energy reshapes the fundamental structure of space-time itself, we find ourselves not as passive spectators, but as active participants in the ongoing cosmic drama of creation and transformation. The most powerful thing in the universe might ultimately be the creative principle that generates this incredible diversity of phenomena from relatively simple mathematical foundations. The capacity for existence itself to explore every possible expression of organized energy, from quantum vacuum fluctuations to hypermassive black holes, from the nuclear furnaces of stellar cores to the mysterious forces that drive cosmic expansion. This recognition transforms our exploration of cosmic power from an academic exercise into a profound appreciation of our place in a universe where the impossible happens routinely, where matter and energy dance together in configurations of breathtaking beauty and terrifying violence, and where the fundamental forces of nature continue writing the story of existence across scales that span from the quantum realm to the edge of infinity itself. The quest for ultimate cosmic power brings us face to face with a profound paradox that has haunted physicists for decades. As we peer deeper into the mathematical foundations of reality itself, we discover that the universe might be powered by something so counterintuitive it challenges everything we thought we knew about energy, matter, and the very nature of existence. Consider the space between galaxies, those vast cosmic voids that appear utterly empty to our instruments. According to quantum field theory, these regions aren't empty at all. Instead, they seethe with virtual particles popping in and out of existence in time frames so brief they exist below the threshold of direct measurement. These quantum vacuum fluctuations represent a form of energy so fundamental that it might dwarf every phenomenon we've discussed combined. The calculations are staggering. Theoretical physicists estimate that the energy density of quantum vacuum fluctuations could exceed the mass energy content of all visible matter by factors approaching 10 to the 120th power. If these predictions prove correct, then every cubic centimetre of apparently empty space contains enough latent energy to power human civilization for longer than the universe has existed. But here's where the paradox becomes truly mind-bending. The same quantum mechanical principles that predict this enormous vacuum energy also suggest that extracting useful work from these fluctuations might be fundamentally impossible. We find ourselves contemplating an ocean of power so vast it defies comprehension, yet so deeply embedded in the structure of space-time that it remains forever beyond our reach. This quantum vacuum energy represents more than just another entry in our catalogue of cosmic powerhouses. It forces us to reconsider what we mean by empty space and challenges our understanding of how energy operates at the most fundamental levels. If vacuum fluctuations contain the energies theoretical calculations suggest, then the fabric of space-time itself becomes the universe's ultimate power source, making every other phenomenon we've explored mere surface ripples on an infinite ocean of creative potential. The implications extend far beyond abstract physics into questions about the nature of reality itself. Dark energy, that mysterious force driving cosmic acceleration, might represent just a tiny manifestation of the enormous energies embedded in the quantum vacuum. The fact that our calculations predict vacuum energy densities trillions upon trillions of times larger than what we observe suggests either a fundamental error in our theoretical framework or the existence of mechanisms we haven't yet discovered that cancel out most of this energy. Some physicists propose that the universe naturally evolves towards states where positive and negative vacuum energies balance almost perfectly, leaving only the tiny residual we observe as dark energy. Others suggest that our observable cosmos represents just one bubble in an infinite multiverse, where different regions have different vacuum energy densities, and we exist in a domain where the energies happen to be suitable for the formation of complex structures. These theoretical explorations reveal something profound about the nature of cosmic power. The most influential forces in the universe might operate not through dramatic displays of violence, but through subtle quantum mechanical processes that shape reality at scales so fundamental we can barely detect their effects. The vacuum energy that theoretically permeates every point in space represents power so deeply woven into the structure of existence that it becomes invisible to ordinary observation. Recent experiments have begun probing the edges of vacuum energy effects through phenomena like the Casimir force, where two conducting plates placed extremely close together experience attractive forces that can only be explained by quantum vacuum fluctuations. These delicate measurements represent humanity's first tentative steps toward understanding energies that might ultimately prove more significant than all the stars, galaxies, and black holes combined. But even as we grapple with the mysteries of vacuum energy, observational astronomy continues revealing phenomena that push the boundaries of what we thought possible through more conventional mechanisms. The recent discovery of intermediate mass black holes has opened new chapters in our understanding of how gravitational power operates across different scales. These cosmic middleweights, containing hundreds to thousands of solar masses, occupy a mysterious gap in the black hole population between stellar remnants and supermassive giants. Their existence suggests formation mechanisms that don't fit our current models of stellar evolution or galaxy formation, potentially involving direct collapse scenarios where primordial gas clouds bypass the normal star formation process entirely. The power implications are extraordinary. If intermediate mass black holes formed through direct collapse in the early universe, they would have released gravitational binding energies equivalent to hundreds of supernovae concentrated into timeframes measured in minutes rather than months. These primordial collapse events might have created the most powerful explosions in cosmic history, briefly outshining entire galaxy clusters, before settling into the steady accretion that characterizes modern black hole systems. The search for these elusive objects has revealed tantalizing hints of their presence in globular clusters and dwarf galaxies, environments where their gravitational influence creates detectable effects on surrounding stars and gas. Advanced gravitational wave detectors are beginning to probe the merger signatures of intermediate mass black holes, potentially revealing an entirely new category of cosmic violence that operates on scales between stellar explosions and galactic phenomena. But perhaps the most intriguing aspect of intermediate mass black holes lies in their potential role as seeds for supermassive giants. The existence of quasars powered by billion solar mass black holes in the early universe has long puzzled astronomers, who struggle to explain how such massive objects could have formed so quickly after the Big Bang. Intermediate mass black holes might provide the missing link, serving as gravitational seeds that grew rapidly through accretion and mergers during the universe's first billion years. This evolutionary connection reveals something fundamental about how cosmic power develops over time. The most extreme phenomena we observe today might represent the culmination of processes that began with relatively modest energy releases billions of years ago. The supermassive black holes that power today's most luminous quasars trace their origins to seeds that formed when the universe was young, and conditions were far more violent than anything we observe in the contemporary cosmos. The realization that cosmic power evolves and amplifies itself over time adds another layer to our understanding of ultimate forces. We're not just cataloguing the most energetic phenomena in today's universe, but tracing the development of power across cosmic history, from the extreme conditions immediately after the Big Bang to the mature structures we observe in the modern epoch. This evolutionary perspective reveals that the question of ultimate cosmic power might depend critically on when you ask it. During the universe's first moments, when space-time itself was expanding at rates that exceeded the speed of light, the power densities achieved during cosmic inflation might have dwarfed everything we've discussed. The energy required to stretch quantum fluctuations smaller than atomic nuclei into structures spanning billions of light years represents forces that operated at the very limits of what physics allows. Inflation demonstrates power through the manipulation of space-time geometry itself, borrowing energy from the gravitational field to drive exponential expansion that created more energy than it consumed. This process essentially manufactured the matter and radiation that fill the universe today from quantum vacuum fluctuations, transforming microscopic uncertainties into macroscopic realities through mechanisms that challenge our understanding of conservation laws. The inflationary epoch might represent the ultimate expression of cosmic creativity, a period when the universe literally bootstrapped itself into existence through processes that generated space, time, matter, and energy from pure mathematical possibility. If theoretical models prove correct, inflation created our entire observable universe from a region smaller than a proton in less than a trillionth of a trillionth of a trillionth of a second. But inflation raises profound questions about the nature of cosmic power that extend beyond our observable domain. Some theoretical frameworks suggest that inflation might be an eternal process, constantly creating new regions of space-time that expand into independent universes with their own physical laws and fundamental constants. This eternal inflation scenario would make our observable cosmos just one bubble in an infinite multiverse where new cosmic domains emerge from vacuum energy fluctuations throughout eternity. The implications are staggering. If eternal inflation operates as these models suggest, then the most powerful process in existence is one that creates infinite numbers of universes, each potentially harboring phenomena that exceed anything in our cosmic inventory. The power to generate not just matter and energy, but entire realities with their own space-time dimensions represents the ultimate expression of creative force. This multiverse perspective transforms our exploration of cosmic power from a survey of the most energetic objects in our universe to a recognition that our entire reality might be just one expression of creative processes operating on scales that transcend individual cosmic domains. The gamma-ray bursts, quasars, and magnetars we've explored would represent local manifestations of power hierarchies that extend across infinite numbers of universes, each testing different combinations of physical laws and fundamental constants. Recent observational hints suggest that our universe's physical parameters might indeed be fine-tuned for the existence of complex phenomena. The strengths of fundamental forces, the masses of elementary particles, and the energy density of dark energy all appear to have values that fall within narrow ranges that allow for star formation, planetary development, and the emergence of complexity. If these parameters had slightly different values, none of the powerful phenomena we've explored could exist. This apparent fine-tuning might reflect the operation of selection effects in an infinite multiverse, where only domains with suitable physical laws can develop observers capable of contemplating cosmic power. From this perspective, we exist in a cosmic domain specifically structured to generate phenomena of incredible energy and complexity, because universes lacking such capabilities don't produce conscious beings capable of studying their properties. The anthropic implications are profound. Our ability to observe and catalogue cosmic powerhouses might itself represent evidence that the universe operates according to principles that inevitably generate extreme phenomena. The mathematical elegance of physical laws, the apparent fine-tuning of fundamental constants, and the incredible diversity of energetic processes all suggest that our cosmos possesses an inherent tendency toward the development of increasingly sophisticated expressions of organized power. In this context, the emergence of consciousness represents perhaps the universe's most remarkable achievement in power manipulation. Through billions of years of cosmic evolution, matter and energy have organized themselves into configurations complex enough to contemplate their own origins, while developing technologies capable of detecting phenomena across the entire electromagnetic spectrum and gravitational wave signatures from the most violent events in cosmic history. We are the universe becoming aware of its own power, matter learning to appreciate the forces that brought it into existence. Every telescope we build extends our sensory reach across billions of light years, allowing us to witness gamma-ray bursts that occurred when the universe was young, detect the gravitational waves from black hole mergers that happened before Earth existed, and map the subtle influences of dark energy on cosmic expansion across the entire history of space-time. This capacity for cosmic observation represents a form of power that transcends individual phenomena. Through consciousness and technology, the universe has developed the ability to study itself across all scales of space, time, and energy. We can probe the quantum vacuum for signs of virtual particle creation, map the distribution of dark matter across galaxy clusters, and detect the afterglow of creation itself in the cosmic microwave background radiation. The instruments we've developed to study cosmic power represent some of humanity's greatest technological achievements. Gravitational wave detectors, sensitive enough to measure space-time distortions smaller than 1,000th the width of a proton. Gamma-ray telescopes that can distinguish between radiation from different classes of cosmic explosions. Radio arrays that can detect the faint echoes of magnetic field interactions around distant magnetars. Each technological advance reveals new aspects of the cosmic power hierarchy, often discovering phenomena that exceed our theoretical predictions. The recent observation of gamma-ray bursts with energies approaching the theoretical limits of stellar explosion mechanisms has forced physicists to develop new models of how matter behaves under the most extreme conditions. The detection of gravitational waves from neutron star mergers has provided unprecedented insights into how the heaviest elements in the periodic table are forged through cosmic violence. As our observational capabilities continue advancing, we're discovering that the universe operates according to principles that consistently exceed our expectations. Every major astronomical breakthrough reveals phenomena more extreme, more energetic, and more creative than previous observations suggested. The cosmos appears to be an inexhaustible source of surprises, constantly demonstrating new expressions of power that challenge and expand our understanding of what's possible in nature. The recent development of multi-messenger astronomy, where gravitational waves, electromagnetic radiation, and neutrino detections provide complementary views of the same cosmic events, has revolutionized our ability to study the most powerful phenomena in the universe. When neutron stars collided in 2017, producing the gravitational wave event GW17-0817, astronomers simultaneously observed gamma rays, X-rays, optical light, and radio waves from the same explosion, creating the most comprehensive portrait ever obtained of cosmic violence in action. This multi-messenger approach reveals that the most powerful phenomena in the universe operate through mechanisms far more complex than any single detection method can capture. Magnetar outbursts generate not just electromagnetic radiation, but also gravitational waves from the stellar surface oscillations they create. Supernova explosions produce not just visible light and gamma rays, but also enormous fluxes of neutrinos that carry information about nuclear processes occurring in stellar cores. Quasar jets transport not just electromagnetic energy, but also cosmic ray particles that travel at near-light speeds across intergalactic distances. The interconnected nature of these phenomena suggests that ultimate cosmic power emerges from the coordination of multiple physical processes operating simultaneously across different scales. The most energetic events we observe result from complex cascades where gravitational collapse triggers nuclear reactions that generate electromagnetic fields that accelerate particles to relativistic speeds that create secondary radiation through interactions with surrounding matter. This systemic view of cosmic power reveals that individual objects or events, no matter how extreme, represent just components in larger networks of energy flow and transformation that span the entire universe. The supermassive black hole at the center of our galaxy influences star formation throughout the Milky Way through its gravitational effects and occasional outbursts. The cosmic ray particles generated by distant supernova and gamma-ray bursts constantly bombard our solar system, potentially influencing atmospheric chemistry and biological evolution on Earth. We exist within this vast network of cosmic power exchange, connected through gravitational interactions, electromagnetic radiation, and particle flows to every other structure in the observable universe. The atoms in our bodies carry the signatures of stellar nuclear processes that occurred billions of years ago. The gravitational waves from distant black hole mergers pass through our planet every day, creating imperceptible distortions in local spacetime that advanced detectors can measure with extraordinary precision. This profound interconnectedness suggests that the most powerful thing in the universe might not be any individual phenomenon, but rather the integrated system of physical laws and processes that enables matter and energy to organize themselves into increasingly complex and creative configurations. From quantum vacuum fluctuations to galactic superclusters, from stellar nuclear fusion to the expansion of spacetime itself, we observe a cosmos where power operates through mechanisms that span every conceivable scale while maintaining mathematical relationships of breathtaking elegance and precision. The fundamental forces that govern these interactions, gravity, electromagnetism, and the strong and weak nuclear forces, represent expressions of underlying symmetries in the mathematical structure of spacetime itself. The constants that determine their relative strengths appear to be precisely tuned to allow for the incredible diversity of powerful phenomena we observe, suggesting that the capacity for cosmic creativity might be built into the deepest levels of physical law. Recent theoretical developments in string theory and quantum gravity propose that these fundamental forces might represent different manifestations of even more basic principles operating in higher dimensional spaces that transcend our ordinary concepts of matter, energy, and space-time. If these theories prove correct, then the cosmic power hierarchy we've explored emerges from mathematical relationships that exist independently of any particular universe or physical domain. This perspective transforms our understanding of ultimate power from a question about the most energetic objects to a recognition that the creative potential embedded in the mathematical structure of reality itself might represent the deepest source of cosmic force. The capacity for existence to generate complexity, consciousness, and wonder from relatively simple mathematical foundations reveals a universe where power operates through principles that extend far beyond individual phenomena into the realm of pure mathematical possibility. As we continue pushing the boundaries of observation and theory, new discoveries await that will undoubtedly challenge and expand our comprehension of cosmic power even further. The next generation of telescopes will probe deeper into space and time, potentially revealing phenomena that operate at energy scales we haven't yet learned to imagine. Advanced gravitational wave detectors will become sensitive enough to detect the quantum fluctuations in spacetime itself, opening entirely new windows into the fundamental nature of reality. The quest to understand the most powerful thing in the universe continues to drive scientific inquiry into realms where mathematics and physics merge with philosophy and wonder. Each new discovery reveals not just more extreme expressions of cosmic energy, but deeper insights into the creative processes that generate the incredible diversity and complexity we observe throughout the cosmos. In this grand exploration of ultimate forces, we find ourselves not as passive observers of cosmic violence, but as active participants in the universe's ongoing project of self-understanding. Through our consciousness, our technology, and our insatiable curiosity about the nature of existence itself, we represent the cosmos developing the capacity to appreciate its own remarkable achievements in organizing matter and energy into configurations that challenge every assumption about what's possible under the laws of physics. The story of cosmic power ultimately becomes the story of how the universe creates, sustains, and transforms itself through processes that operate across scales, from the quantum realm to the edge of infinity. In contemplating these ultimate forces, we're engaging with the deepest creative principles in nature while recognizing our profound connection to the ongoing cosmic dance of energy and matter that continues writing the story of existence across all the dimensions of space and time. The search for ultimate cosmic power takes us beyond individual objects into realms where the very concepts of space and time begin to break down. We're about to encounter phenomena so extreme they exist at the theoretical limits of what mathematics can describe, where the familiar laws of physics merge into unified descriptions of reality that push human comprehension to its absolute breaking point. Welcome to the domain of hypermassive black holes, objects so colossal they challenge our understanding of how matter and energy can organize themselves under the influence of gravity. These theoretical giants would contain masses exceeding 100 billion suns, approaching the point where their own gravitational influence begins to affect the expansion of space itself within their immediate cosmic neighborhoods. The physics governing hypermassive black holes ventures into territory where general relativity encounters quantum mechanics in ways we're only beginning to explore. At these extreme masses, the event horizon would encompass regions larger than entire galaxy clusters, creating gravitational fields so intense they could strip matter from neighboring galaxies across distances measured in millions of light years. But here's what makes hypermassive black holes truly extraordinary from a power perspective. Unlike their smaller cousins, these objects would operate in regimes where the distinction between local gravitational effects and cosmic expansion becomes meaningless. They represent gravitational systems so massive they begin to resemble miniature universes, complete with their own internal space-time geometries that might be causally disconnected from the rest of the cosmos. Recent theoretical calculations suggest that hypermassive black holes, if they exist, could have formed only during the universe's earliest epochs, when matter densities were high enough to enable direct gravitational collapse on scales that dwarf anything possible in the contemporary cosmos. These primordial monsters would represent fossil remnants of conditions that existed when physical processes operated under rules dramatically different from those governing modern astrophysics. The power implications are staggering. A hypermassive black hole would influence the structure and evolution of space-time across volumes containing thousands of galaxies. Their gravitational effects could determine the large-scale architecture of cosmic structure, creating vast regions where normal galactic evolution becomes impossible due to tidal forces that tear apart star-forming regions before they can collapse into stellar systems. Yet even these theoretical giants pale in comparison to phenomena that exist at the absolute frontier of physical possibility. Planck-scale black holes represent objects where quantum mechanics and general relativity achieve perfect unity, creating conditions so extreme that our current mathematical frameworks begin to lose their descriptive power entirely. At the Planck scale, roughly 10 to the minus 35th meters, the very concept of smooth spacetime breaks down into a quantum foam of virtual particles and fluctuating geometries. Black holes at these scales would contain masses approaching the Planck mass, about 22 micrograms, yet compressed into volumes smaller than atomic nuclei. The power densities achieved in these microscopic monsters would exceed anything we've discussed by factors that require entirely new forms of mathematical notation. Planck-scale black holes demonstrate power through their ability to exist simultaneously in multiple quantum states, creating superpositions of gravitational fields that violate our normal understanding of how space-time behaves. These objects represent the ultimate fusion of quantum uncertainty and gravitational determinism, existing in states where cause and effect, past and future, matter and energy all become indistinguishable aspects of more fundamental mathematical relationships. The theoretical framework describing Planck scale phenomena suggests that reality itself might be quantized at the deepest levels, with space and time existing as discrete units rather than the smooth continuum we observe at larger scales. In this quantum spacetime, black holes become mathematical objects that encode information about the fundamental structure of existence itself, demonstrating power through their capacity to manipulate the basic building blocks of reality. But perhaps the most mind-bending possibility in our exploration of ultimate cosmic forces lies in the theoretical existence of white holes, objects that represent the time-reversed solutions to Einstein's field equations. While black holes absorb everything that crosses their event horizons, white holes would explosively reject all matter and energy, creating fountains of radiation that emerge from apparently empty regions of space without any observable source. The theoretical power output of white holes transcends every category we've established for measuring cosmic energy. These objects could, in principle, create matter and energy from the quantum vacuum itself, generating particles and radiation through processes that appear to violate conservation laws while actually exploiting the deepest structures of space-time geometry. A white hole could produce the equivalent energy of entire stellar explosions continuously, without any apparent fuel source or limiting mechanism. White holes represent the ultimate expression of cosmic creativity, objects that demonstrate power not through the conversion or concentration of existing energy, but through the spontaneous generation of matter and radiation from the mathematical structure of space-time itself. They would operate as cosmic geysers, erupting with energies that could dwarf quasars while drawing their power from sources that exist entirely outside our normal understanding of how energy flows through the universe. The search for white hole signatures has become one of the most speculative frontiers in theoretical astrophysics. These objects would produce electromagnetic emissions unlike anything generated by conventional processes, creating bursts of radiation that appear without warning from regions of space that show no prior signs of unusual activity. The challenge lies in distinguishing genuine white hole phenomena from other exotic possibilities that might produce similar observational signatures. From quantum foam to cosmic acceleration, from stellar forges to the mysterious forces shaping space-time itself, our journey through ultimate power has revealed a universe far stranger and more magnificent than we ever dared imagine. We've witnessed black holes that outmass 60 billion suns, explosions that briefly outshine entire galaxies, and forces so subtle they determine the fate of everything that exists. Yet perhaps the most powerful discovery of all is this: we are not separate from these cosmic forces, but made of them, temporary arrangements of stellar debris that have achieved the extraordinary ability to contemplate the very powers that created us. The universe has spent 14 billion years learning to understand itself through our eyes, and that recognition might be the most powerful thing of all.